Good afternoon, ladies and gentlemen. John's rattled through quite a bit of information, the background to the engineering decisions and motivations to worry about good grade steel. And my job's to talk a wee bit about some of the lessons that we learnt from the commercial buildings. Funny enough, engineers get excited about thousands of cracks in walls, and thousands of cracks in walls is a good thing because it actually means the reinforcing the client's paid for is actually doing its job. And we do really like to see lots and lots of cracks. That's the same wall that's been epoxy injected, and I just realised I missed my calling in life. I should have actually got into epoxy injection because at about $200 a linear metre, I think that wall comes out around about $14,000 to inject. I think the wall's only worth about $9,000 to start with, so maybe a better idea was to knock it down and build a new wall. But that's the sort of thing we're actually looking for. Lots and lots of cracks, dissipating the energy, stretching the walls, and the reinforcing doing its job, and a ductile reinforcing at that. This is the 123 Victoria Street. This is actually John and my building. We're actually on the 5th floor of this when it hit. And the wall down the bottom had no cracks in it. Everyone went, woohoo! And the reason we had no cracks in it, because it probably wasn't connected to the floor very well. Large stair well, large lift well. This wall wasn't really connected, so it didn't get hammered. But its sister wall on the other side did. And this is looking from inside the building at the wall. End of the wall's got like a mini column cage in it. The wall's buckled. Me and my usual overzealous theatrics would reckon we had about another 10 to 15 seconds before we turned into PGC. This wall's on the way down. And a big red arrow at the top is the boardroom where I was when the earthquake hit that February day. And I can remember going over the top of the boardroom table, hitting the wall on the far side, thinking about the Coca-Cola I just spilled on the carpet. No, I was going to get yelled at by the lady on the front desk for spilling the Coke. And there I am on my belly trying to get out of the room, and of course we had so much vertical as well as horizontal, it was sort of like watching one of those kids' toys, and elbows and knees, I was just sitting there doing this. Eventually the earthquake stopped and we managed to get out and evacuate everyone out of the building before the next couple of big aftershocks came through. But this is actually looking at the outside of that wall. I'll go back. This is the inside, looking from the inside of the building on the ground floor. This is looking at the same wall from the outside. And what's missing is stirrups. Now, they're not missing at all. They were never asked for in the New Zealand codes of the day. And in fact, they're not even in the current New Zealand codes for designing concrete structures. And funny enough, they've actually been in the European codes for about 10 years, that you need to put stirrups through your wall to hold the concrete in. And there's a little one down here, a little orphan stirrup all by itself down here doing its job, holding that bar. And what the idea is that the two cages of horizontal and vertical steel on either side of the wall, if it's constrained by stirrups passing through, the big pieces of concrete don't fall out. The big pieces of concrete don't fall out because the lightweight steel in the wall can't hold it in. If the big pieces of concrete are held in place, the wall will still carry load. But once it wasn't so much the reinforcing got overloaded, the concrete fell out, and there was no way of the forces passing through the wall when the concrete was gone. Another example of the same sort of problems we're having, this is an apartment building, Park Terrace area. A couple of things to note. That dark shading area there is one very, very large crack, not the thousands of cracks we're looking for. So when that building tilted over, all the stretch occurred on one crack, and what we ended up doing is breaking. It's hard to see up here, but what we've actually got is broken main bars. Vertical bars have snapped. Because all that movement in the building occurred at one crack, and not over a whole lot of cracks. And even with good reinforcing, it's too much to ask of it. So not only is it a reinforcing problem, but it's a design problem. And there's some recommendations out there now in the industry on how to make sure for new buildings moving forward that we have enough reinforcing steel to create lots and lots of cracks, which dissipates the stretch on the bars, all over the length of the bars. The other thing we found too, which was a wee bit of a worry, when the outside skin of concrete fell off, there's air in there. When the outside skin of concrete fell off, traditionally and around the world, all the horizontal bars are just simply lapped inside the concrete. And when the cover concrete fell off, those laps failed. When the laps failed, one large crack opens up and the wall shits itself. What's on the left is what we like to see. A nice lot of crack patterns with the bars being stretched over a very, very long length. That stretch accumulates, so any one particular crack, the bars aren't overly stretched, overly strained. The idea is to have a distributed lot of cracks. The big problem is when you have a wall say, a construction joint rocking onto its tip and stretching one bar by itself, or one layer of bars at one crack, should I say. Here's a case in point. This is known as the Gallery Apartments, and it's right immediately to the east of the Art Gallery, which was the emergency operations centre for February and September. And after a few days, the word went out that someone had noticed, another academic colleague of mine, Professor Andy Buchanan, who's actually a timber guy, so 5 points to Andy for spotting a problem with concrete, got a phone call from him saying, I think we've got a problem. I said, what's that, Andy? He says, I'm on top of the art gallery looking at a wall and there's only one crack. I said, that's a good thing. He said, no, it's not. I said, I've done the numbers in his head. And he worked out that that crack might have been quite large. In other words, the top of the building moved a long way. And when I said, well, the only way we're going to find out is to bring in a team, so I was actually part of search and rescue at this time, and John did his time in that as well. Called into search and rescue and said, I need a squad up here to open up the wall, bring some Kangos. So the New South Wales Aussie team turned up, bless them, and they took out the concrete off the end, and that's the commander of the Aussie squad's hand. And there's a bar there and a bar there, and they're overlapping. And by this stage, about 5 engineers had turned up. All had an opinion. There's a bunch of rules around, several very, very, very good guidelines around the world. One of them is from FEMA, from the United States, the Federal Emergency Management Agency. And they say if you've got one crack and it's less than 5 mils wide, just epoxy inject it, don't worry about it. Well, this crack was hairline, but what Andy was expecting to see was a whole lot of cracks, and he only saw one. So he started to get worried. And when we opened it up and had a look at it, that's the lap. And the first engineer says to me, that's a funny looking lap. Well, normally that lap for that size bar is about 400 mils. I said, take a look at the shape. The shape's conical. The bars come to a little tip. What's happened is the bars have stretched at one crack and ruptured, fractured. And that's the shape you get when the bars have been taken to the point of snapping. So what we found was first impressions, and this is a bit of a lesson for all of us engineers and building inspectors, is at first impressions, you've got to be a bit careful. One single crack, no one was getting too worried for the first 4 or 5 days. But Andy stood up there, looked at the building, and worked out it probably moved about half a metre to 700 mils at the top. And when he worked out what that meant at one crack at the base of the wall, the crack had probably opened up about 40 mils. Then the building come back down, the wall sat back down on itself. That meant that most bars like that will fracture about 15 to 16 mils, and he probably did it in his head and reckoned it got to about 40 mils, and that's why the bar fractured. Now, the next part of the story is, the next engineer says, oh, we always know that it's just the ends of walls this happens at. So the Aussie looked at me and said, yeah. So they went along the covered concrete, right along the wall, and every bar was broken. And they started opening up the next wall, and the bars were broken. So this set off a major set of alarms, not just for New Zealand engineers but worldwide, that maybe we don't have enough steel, vertical steel in the walls, to get that good fan crack, distributed cracking pattern, which is what we need when we're looking for ductile structures that can deal with earthquakes. So this has actually been an international lesson. That was just one of the other silly areas of the same building, a different wall. Normally this wall would have stirrups about every 150, 175 millimetres. They're about 400 to 600. And what happened was, that's my thumb and a pen, it just shows you how far the bars buckled out. Again, if the earthquake had continued, we would have probably lost that building. It's 11 stories high, and it was no doubt, I guarantee you, that would have fallen through the art gallery and taken out most of the base of operations. We're just going to take a look at another case study, the Clarendon. You guys know the Clarendon in town. It's down now. They did a very good job at taking it down too. Take my hat off to the guys. But what this is, a concrete frame around the outside, no walls on the inside, just jib and stud around the lift and stair shafts. We're going to take a look at this corner. And this is looking on the corner. That's the beam to one side, and there's a beam here. And what we know about in earthquakes, particularly for reinforced concrete beams, is when they get stretched in an earthquake, when they get worked in an earthquake, they get longer. And that lengthening, because the bars are yielding, it's like a paperclip. If you ping a paperclip, it's elastic, it stays the right shape. If you bend a paperclip, it's called plastic, or it's yielded. And what happens when a bars yield, they lengthen, they stretch. And what happened is, people originally said, oh, the floor, there's a big crack here along that beam, the floor's moved away from the column. No, what's actually happened is the beams have all lengthened and pushed the corner column out of the building, leaving the floor behind, which is a bit of a problem When you're looking at, this is the column here, which has been pushed out to the northwest. This is a beam here. The floors are spanning in the direction of the arrow, and there's a rule I threw down. Gives you an idea, and this is seen the shot already from John, 35mm tear. The cold drawn wire mesh broke at probably somewhere between 2 and 6mm stretch. Even a conventional reinforcing bar can only handle 15 or 16 mils. So this is 35 mils, and we're in shit street. This is a real problem for the older style floors. This is looking into another part of the building. This is looking on the same building but the middle bay, and there's a beam there where the red dot's running, and there's the beams along that frame line there. It's that frame line there. All these little beams stretched, and what happened was this part of the building got pushed out to the west, and that part of the building got pushed back to the east. We ended up with a large tear around the blue square, which is the middle floor. Now, it doesn't help that in September, when we had the earthquake and damaged the floors a little, that the contractor, in his defence, he didn't know any better, stuck 4 tonnes worth of carpet tiles onto that floor area. And so, needless to say, when the earthquake decided to find the Achilles heel in the floor, all that extra weight didn't help things at all. And that's about a 25mm crack looking through the downstairs. That's the room below, and as the earthquake and aftershocks came through, we were able to read the newspaper that was on the floor below. The next shot is the floor. This floor, not only did it tear this way, but it dropped about 35 mils. And it's basically hanging on by a whisper and a prayer and a few cobwebs. If you do the mathematics from the engineering, everything that knows about engineering, that floor shouldn't be there. It's a 7th floor. It's not a particularly good look. It just hung on, and that's just me in the background in nice iridescent fluoro. So what we're looking at is we really do need, it's more than the reinforcing, but one of the critical features of the reinforcing is to make sure that it can handle unforeseen stretches. Engineers make really good educated guesses. I'm probably not allowed to say that in public, John? But fundamentally, we know a lot about engineering, a lot more after the February earthquake. The world does. I mean, it's been a $30 billion laboratory out there. But, you know, earthquakes don't read the codes. They'll shake the shit out of your building, find the Achilles heel, and bring it down and kill everyone in it. And so the idea is to build some toughness, some robustness, materials we can rely on. And one of the things that has really come to the party in these earthquakes, both the residential and commercial, is that we need a good grade ductile steel. Now, before I jump on to the last couple of slides, there's only 2 slides to go. John talked about a ductile mesh, and I'm just going to add a little codicil to that, the true ductile mesh, not the old ductile mesh. There's a brand out there called ductile mesh. It's very, very old. It's actually brittle as hell. So what you'll often hear in a conversation amongst engineers, the new ductile mesh or the true ductile mesh. Sounds like something out of True Blood or Star Wars, doesn't it? But it behaves like, it's a mesh system that behaves like a conventional, good quality seismic E-grade bar. That's what you're looking for now, to cover your bases. The things that engineers get really excited about, funny enough, we really do like to have the columns, for example, tied up with lots and lots of stirrups. No, I don't own any shares in Pacific Steel. I'm not here for my own gain. The idea is that if you've got a modern structure with nicely close-spaced stirrups and lots of bars around the outside, the white core of the column stays intact. It's the same problem we had with the walls. If we don't have these stirrups, the column balloons, explodes, and can't carry the gravity, and gravity is very, very unforgiving. So we tie columns up, and now we're tying up the walls in the same way of holding, confining, or constraining everything into the centre of the member. Want to do the same with beams too. This is a look cross section through beams. Beams, when the bars get stretched and work, develop lots and lots of cracks out through the cover concrete between themselves. Unless you've got a really good layout of reinforcing, those bars will fail or slide. The laps, where the bars are basically joined in the concrete, will fail like they happened in the wall. By the way, those laps failed in the wall, and that's most of the walls, long walls in New Zealand are designed that way, with just laps sitting in the concrete without stirrups going across. Now we would either hook the bars so they run past each other, or make sure they're stitched up with some form of stirruping. Same with columns. You always typically lap a column above the floor. That's the easiest way to build them. The column cage comes in on a crane, it lands down inside the one that's already been cast in the floor below, and as long as there's a decent number of stirrups around the lap, the column will go forever. It's ductile, good and ductile. So it all comes down, a lot of it, not just the quality of the reinforcing, but what engineers actually do with it. In summary, reinforcement is there for more than just the in-service design loads, which I've sort of been bleating on a wee bit about already, in terms of it's a whole system. It's not just one particular thing's going to lead to problems with the building. It's how the concrete, the way the floors are set on the beams, the way the walls are tied into the foundation, everything must be tied together. Ductility is important for more than just the direct design actions, meaning what that comes down to is we like the bars to stretch. It uses up the energy of the earthquake. We like thousands of cracks because then we stretch the bars over a decent length without concentrating all that stretch at one crack, and we've seen the problems of stretching at one crack. It also means if we have ductility in the system, if the earthquake hasn't read the code and the building gets shook in such a way that we haven't allowed for, the building is tough enough to ride it through. And a lot of the modern buildings, as John said, post-1995 buildings, had that toughness in them, inherent toughness, that robustness, and allowed them to ride some of the biggest earthquakes, if not the biggest accelerations ever recorded in a modern city. I mean, those earthquakes in February were freaking huge. Okay, so again, it's how the ability for the systems to ride through those earthquakes, it comes down to the quality of the materials and how they're put together, design and contracting as well. Detailing is critical. I've alluded to stirrups and so forth, little stories around that. And the other thing is specifying the right steel in the right place. And John's already said it, really as a practice now, we wouldn't go for anything less than E-grade seismic style steel in our structures, simply because of these earthquakes have told us that parts of the structure you normally would have assumed to be unstressed have got hammered. And that's it. Thank you very much.